up to this point, we've been looking at univariate situations. In other words, whenever we've looked at distributions, we've looked at the distribution of a single random variable. But in the real world, often we're not concerned with just a single random variable, but we're often interested in the distribution of multiple variables together, or what we're going to look at here primarily are bivariate situations. So as an example, suppose that we have 12 cards numbered 1 through 12, and we're going to select 2 cards at random without replacement, and then we're going to define here 4 different random variables. So x is going to be the number on the first card, y is the number on the second, z is going to be the difference in the numbers, so notice that z is going to depend on both x and y, and then w is going to be equal to 2x plus 3y. And so the first thing we want to do is we want to find the probability that x is equal to 2 and y is equal to 5. So notice here we have cards that are numbered 1 through 12. So when we go and we draw the first card, the probability that card is going to have a 2 on it is just going to be equal to 1 out of 12. Now when we go to draw our second card, notice since we're sampling without replacement, we have 11 cards left in the deck. We know that, we're looking at the probability the first one was equal to 2, so we know 5 is still available. So the second one is going to be 1 out of 11. And we could write this as follows as well. So in general, for this example, if we want to know the probability that x is equal to lowercase x and y is equal to lowercase y, it's actually going to be equal to the same value. And this is for x is equal to 1 all the way to 12, and then x not equal to y. And then y is also equal to 1 through 12. And so this is an example of a bivariate discrete probability distribution. So definition here, let x and y be discrete random variables. The joint or bivariate probability distribution for x and y is given by the following. And there's no reason we have to limit this to just 2 random variables. We could extend this, to past 2, and then we would call it a multivariate distribution. But again, for simplicity here, we're going to primarily focus on bivariate. And notice this is defined for all real numbers x and y, and then that function will be referred to as the joint probability function. So we have a couple properties of the joint probability function, and you're going to notice that these are very similar to very similar to properties that we saw in the univariate case. So for example, the probability of x and y is going to be greater than 0 for all x and y. We could also say here, since that is a probability, we also know it's going to be less than or equal to 1, very similar to the univariate case. And then if you recall in the univariate case, when we summed over the entire sample space, or we summed the probabilities over the entire sample space, we defined that was equal to 1, and the same thing is going to happen here. Now one thing to note is when we work with discrete distributions, this is sometimes called the joint probability mass function, similar to when we looked at the PMF or probability mass function before. And again, the idea here is that it specifies probability or mass associated with each point. And so that's true for discrete random variables, but that is not true for continuous random variables. Alright, so we can find the probability that x is greater than or equal to 1, less than or equal to y, less than or equal to 3 for the previous example. So one way to help us visualize that is we could draw a table here to the side. Along the top, I'm going to write down the possible values for y. Along the side, I'm going to write the possible values for x. And then looking here at where these intersect, let's think of what some of these possible values could be. So, for example, what are the possible values if x is greater than or equal to 1 and y is less than or equal to 3, but we also have the restriction that y has to be greater than or equal to x. So, notice here, if we have the restriction Well, first of all, notice that we can't have x and y be equal to the same number. And the reason for that is remember for this example, we have 12 cards. There's numbers 1 through 12. We're sampling without replacement. So there's no way to pull a 1 on the first one and a 1 on the second one. So anything that involves the same number twice is out of the picture. We can't have that. Now, if x were equal to 2, is it possible for y to be equal to 1? And the answer here is no. We can't have x is equal to 2 and y is equal to 1. So that one is also out. Alright, and notice then if x is equal to 3, there's nothing for y to equal. So these are all going to be out as well. Now, if x is equal to 1, could y be equal to 2? Yes, that would satisfy. If x is equal to 1, y could also be equal to 3, so that one's satisfied. Also notice y can't be equal to 4 by our restrictions. And then finally, if x is equal to 2, y can be equal to 3. So notice there's really only 3 different possibilities here. So, the probability that we're interested in is equal to p of 1, 2 plus p of 1, 3 plus p of 2, 3. And remember before we saw that all of those were equal to 1 divided by 132, so this is equal to 3 divided by 132. We could also define CDFs. So for any random variable x and y, the joint bivariate distribution function, capital F of xy, is given by the following. So notice here we've got the greater than or equal to's. So for our previous example, we could find f of 2, 3. So notice here f of 2, 3 is equal to the probability that x is less than or equal to 2 and y is less than or equal to 3. So notice in this case the value of y and x are not dependent on one another. We're just looking for all of those which x is less than or equal to 2 and all of those which y is less than or equal to 3. And you could look up at the chart up above and notice there are 4 different possibilities here. And then again, remembering that each of these is equal to 1 divided by 132, we have 4 divided by 132. We could do something very similar for continuous random variables, except instead of summations, we would be looking at integrals. And so since we have 2 random variables, we're actually looking at a double integral here. And that should actually be dy dx by the way that's written. And then similarly we could look at properties of the CDF. Again, recall that the CDF is given by the following. And we have the following properties. So again, in the univariate case, we saw that as we went to negative infinity, the CDF went to 0. Well, in this case, as both of the random variables tend towards negative infinity, the CDF goes to 0. As we go to positive infinity for both random variables, CDF will go to 1. And then we also see that it is non-decreasing, except it's now going to be non-decreasing, but looking at the 2 random variables, and we can see that in property 3. So consider the following, and this will go along with number 3 here. I'm going to draw a table. Here I'm going to have y, and here I'm going to have x. So first, x could take 2 different values. We're going to call them a1 and a2. Y could also take 2 different values, and we're going to call them b1 and b2. So let's consider 4 different regions here. We're going to have region 1, region 2, region 3, and region 4. All right, notice if we look at FA2, FB2. So in other words, we're interested in the probability that x is less than A2 and x is less than B2. Notice that's actually going to be all of the regions. Now, let's subtract off f of A2, B1. And this is going to be the case where x is less than A2 and y is less than B1. So what we're doing here is we're subtracting off regions 3 and regions 4. Pardon me. We're subtracting off regions 2 and region 3. Then we could subtract off f of A1, B2. Well, if we're less than A1 and less than B2, that's going to be subtracting off region 3 and region 4. And then if we add back on f of A1, B1, that's going to correspond just to region 3. So notice if we do this, what we're looking at is this equation right here. So notice, looking at the cancellation, everything cancels out here except for region 1. Well, let's go back and look at this probability. So this probability looks at x between A1 and A2 and b between B1 and B2. In other words, this region right here. So that's what we're left with. Here's a visualization. Now, one thing to keep in mind with bivariate, what we're looking here is that f of AB is going to be the volume now under a curve. So we are looking in three-dimensional space instead of two-dimensional space, which is what we were looking at when we looked at the univariate case. And then just to make this match what we were looking at before, this y1, that is actually x, and the y2 is the y. Next, let's look at a continuous example. So the properties of lowercase f of xy, if x and y are jointly continuous random variables with joint density function, then the following holds true. Well, we know we're always going to be greater than or equal to 0. We never dip below the x-axis, or in this case the xy plane. And then we also know if we integrate over the sample space of both x and y, that is going to have to be equal to 1. So just like before where we saw the area under the curve was equal to 1, now again we're in three-dimensional space, so the whole area under that region is going to be equal to 1. So let's look at an example here. So here we have our joint density function, and we're going to start off by finding capital F of 1/2, 1/4. So you always want to start by graphing the region over which you're going to integrate. So what we're really going to be plotting here is that xy plane, and then we're going to integrate over that plane. So here we're going to start out with our region. We've got x and we've got y. And notice that we're interested in x less than 1/2, and we're interested in y less than 1/4. Okay? And so the region that we're integrating over is going to be this region right here. Alright, so if we want to find f of 1/2, 1/4, again, remember that that is equal to the probability that x is less than or equal to 1/2 and that y is less than or equal to 1/4. And so we're going to need to integrate both with respect to x and with respect to y. So in the outer integral, we're going to do x. So x is going to be integrated from 0 to 1/2. Y is going to be integrated from 0 to 1/4. Here we have our function. And we're going to integrate with respect to y and x. Alright, so doing so, we get the following. First, integrating with respect to y. And we do get some cancellation here. So this is going to be equal to the integral from 0 to 1/2 x times 1/4 squared plus 1/4 cubed divided by 2 minus x times 0 squared minus 0 cubed divided by 2 dx. And so notice this is going to be equal to the integral from 0 to 1/2 1 over 16x plus 1 over 128 dx. Now integrating with respect to x, we find the following. And then you can confirm, since I'm running out of room here, that is equal to 3 divided by 256. Alright, we could also find the probability that x plus y is less than 1. So let's see what that would look like. And again, the first thing I'm going to do is I'm going to draw a picture of the region over which I'm going to integrate. Now we know that both x and y are restricted between 1. And notice that this dotted line here is the line x plus y equal to 1. So if I want x plus y to be strictly less than 1, really what I'm doing is I'm integrating over this space right here. So now, to find the probability that x plus y is less than 1, again, I'm going to look at a double integral, but notice that my limits of integration, or what I'm integrating from, whether I start with x or I start with y, they are going to depend on each other. And so here's what I mean by that. So notice this is equal to this integral. The region I integrate over for x, is going to depend on y. So in other words, how far I go over on the x-axis is going to depend at what position I am at y. So this is why here we integrate x from 0 to 1 minus y. Alright, so now we can perform that integration. And I'm actually going to let you confirm this on your own. So you should find that this is equal to 5 divided by 24. And if you have any problems with that integral, just let me know, but it's going to be very similar to what we just looked at on the previous example. Right, so we could generalize this to n random variables where we're only looking at 2, and here's what that would look like if we generalized it. Next, we're going to look at what is known as marginal distributions. So we can use the joint probability distribution of x and y to find the marginal distribution for either x or y. And so let's look at an example here. So here we have x equal the outgoing local phone calls, and y is going to equal the outgoing long distance phone calls from a company during a 5-minute period. And suppose that the joint probability distribution is given as follows. So again, x is going to be local phone calls, so we have x going this way, and this is long distance. Alright, so we could find the marginal for x and the marginal distribution for y. So, in order to do this, what we're actually going to look at are the row and the column sums for our table. So let's start out by looking at that marginal distribution for x. Notice that x can take 4 different values, 0 through 4. So, if we want to look at the marginal of x, let's just say it's 0, what we're going to do is we're going to look at the probability x equals 0 across all the possibilities for y, which are 0, 1, and 2. So in other words, the probability that x is equal to 0 is equal to the probability that x is equal to 0 and y is equal to 0, the probability that x is equal to 0 and y is equal to 1, plus the probability that x is equal to 0 and y is equal to 2. So notice we can actually use this first column to help us out. So really, the first column sum, what that's giving us is that is giving us the marginal distribution at x when x is equal to 0. And we could see something similar for the other column totals. So then we could write the marginal distribution of x as a table. And then we could do something very similar, and we could find the marginal distribution of y by looking at the row totals. And then of course, we know that the overall total must be equal to 1. So let x and y be jointly discrete random variables with probability function p of xy, then the marginal distributions of x and y are respectively given by the following. So notice what we're doing to find the marginal of x is we're summing over the possible values for y, and then to find the marginal, this should be a y right there, the marginal distribution of y, we're summing over the possible values of x. And then we could do something very similar in the continuous case, and for the continuous case what we're going to do is we're going to integrate over the other value. So let's look at an example of that. We've seen this distribution before, so we're going to find the marginal distributions for x and y. So we'll start out with the marginal for x. So first, notice that x exists between 0 and 1. So to find the marginal for x, what we're going to do is we're going to integrate over the sample space for y, and y exists also between 0 and 1. So we're going to integrate from 0 to 1, 2xy plus 3 halves y squared dy. This gives us the following. We do have some cancellation here. So this gives us the marginal for x is equal to x plus 1/2 when x is between 0 and 1, and it's equal to 0 otherwise. We could do something very similar to find the marginal distribution of y, and I'm going to let you try this one on your own, but you should find that the marginal distribution of y is equal to y plus 3 halves y squared, y between 0 and 1, and 0 otherwise. And then we could always check to see whether or not these are valid. So for example, for the marginal of y, we could integrate this function over the sample space of y, which is 0 to 1, and ensure that that does integrate to 1. And if you do that, you will find that it does integrate to 1. And that's going to end this set of notes.